Greetings everyone, welcome to Side A, Side B. This is our first video of the year. We hope everyone is well. In this video, prove a foundational theorem of geometry. The overall plan, develop a line of thought supported by axioms and other theorems. So what's in our toolbox? How about straight up algebra and geometry? Like we said, we want to prove a geometry theorem that's attributed to Thales of Miletus from around 600 BC regarding proportion between two similar triangles. He's also known as an astronomer. It's believed he calculated the height of a pyramid using his work. This is actually the idea of a three-dimensional metric space. We can generalize the definition of a metric space as a set, which comes equipped with a function called a metric, which measures distance between points. For example, three-dimensional space is a set of three values which is required to determine the position of a point. The metric is the following distance function for 3D space, commonly known as three-dimensional Euclidean space, which can model physical space. That's very practical because we can study three-dimensional objects in the metric space, such as defining an object and then perhaps redefining it simply by changing values. Otherwise, we'd have to create objects, which would make a learning process very cumbersome. Notice the distance of the perforated line d sub 1 in the blue circle. Let's find its value to demystify the equation. In 2D space, we use the following formula to calculate the distance between P2 and P1. So let's break it down. On a line, we calculate distance between E and F by equation 1, which is the absolute value of F minus E. Equation 2 might look familiar, is the Pythagorean theorem, solved for D1. Let's use the formulas to solve for D1. Our graph now has lengths A and B defined. Notice A is the distance between x1 and x2. B is the distance between y1 and y2. Then let A equal the absolute value of x2 minus x1. Similarly, we can do the same for B for the y values. Now use equation 2. We have that d1 squared equals a squared plus b squared. Then square root both sides. We get top and bottom equations are a match. Now we can calculate the distance between P1 and P2. Nice. Let's calculate the distance between P1 and P3, named D2, the purple line. Now all 3 points have new coordinate Z. We have another right triangle with new sides D2 and C. See that? Then we can use the Pythagorean theorem again. Set up the formula as follows. Letting C equal the absolute value of Z2 minus Z1. Next, since we know D1 squared equals A squared plus B squared, we can make the appropriate substitutions. Then, square root both sides. The top and bottom formulas are a match. Thales' theorem is precise, yet at the same time may have unknowingly showed a relationship between illusion and reality. Is visual space a metric space? Just consider a paper by the following people. Notice, it's an open question. But in spite of the title, It reveals a possible way to think of visual space in terms of their own unique spaces. For example, in figure 1a and b, it seems apparent visual space has two different spaces, horizontal and local. From the horizontal perspective, lines converge to a point, like in non-Euclidean geometry. It's possible parallel lines fail, yet in geometry they work. Because just consider two perpendicular lines in Euclidean geometry will never converge no matter how far we extend the distance between them. Whereas we do the same in non-Euclidean geometry. It's possible to get two cases. First, the lines will converge. Second, the lines will equal each other. But it's possible to have two straight lines, L1 and L2. They'll never converge, with the condition that the circumference of L2 is less than L1. Since the evidence supporting the shape of the Earth is spherical, is numerous and compelling, we'll say it's a give and condition situation. Just take a look at a globe with longitude and latitude lines. It shows it's a given that a road never converges, along with the condition that we'll have to drive on a slant. Or it's a given the lines equal each other, along with the condition we'll come face to face, the road converging. That would be quite stunning for sure. In other words, it's like a blend of illusion and reality. The apparent reality happens on a large scale. The illusion could be we don't feel the effects on a local scale, which is actually nice. In the horizontal, seemingly parallel lines will converge. We know on a large scale this is true, but at the same time, it's impractical on a local scale. But then we have to conclude the road is slanted. Yet again, we don't entirely feel the effects of a slanted road locally. In both cases, it's like a blend of apparent reality and illusion. However, in figure 2, it shows it's possible Euclidean geometry could be defined on a micro-local space within the square area. It follows the metric is the distance formula in 3D. The problem arises is how to define a metric in the horizontal set, as it's a blend of reality and illusion. At the same time, it seems logical to break visual space into two sets, as in the horizontal, the more abstract, versus local, the more friendly. On that note, we define the entire local space also into two sets, but rename them as follows: horizontal as local macro and local as local micro. The paper basically concludes, quote, "In fact, considering perceived distance, one of the apparently most elementary aspects of visual space, it has been shown that it, whether egocentric or exocentric, does not have a simple relationship with its physical counterpart," unquote. Where ego is our perception and exo is independent of our perception. Put differently, in the example we used, apparent reality is exocentric, whereas locally it's egocentric. Such as we represented a path in physical space from a viewpoint independent of us viewing it on a map, which is exocentric, and then from the point of view of a traveler moving along the path, which is egocentric. Combining our example with their work, it shows there doesn't seem to be a simple relationship between exocentric and egocentric distance either. Also, neither on a local level, by two apparent ways to visualize local events, one macro, the other micro. But what if we could simplify? As it were, a blend of illusion and reality. Let's begin. Welcome back. Looks like we have the task of blending illusion with reality using a mathematical argument. Thanks a lot. First, we can use an axiom, which is the transitive property, which is if x equals y and y equals z, then x must equal z. For example, if an area of a triangle x equals the area of a triangle y, at the same time, the area of triangle y equals the area of triangle z. It follows the area of triangle x must equal the area of triangle z. Seems straightforward enough, and it's an axiom, so we don't have to prove it. So let's move on. We're calling axiom 2 defining parallel lines, where they never intersect, regardless of how far they are extended by the yellow arrows. They also maintain the same distance apart at all points, which means the perpendicular distance between parallel lines is always constant, such that if you draw a line H perpendicular to one of the parallel lines, it will intersect the other parallel line at a constant length equals H. Assuming we have parallel lines, then this axiom holds. Before we discuss Thales' theorem, we need to prove some other theorems which will support our work. So here's a proof of a formula that we're speculating many take for granted, including side A, side B, until now, which is prove the classic formula length times width equals the area of a rectangle. First, for any b and n, where b is less than n or n is less than b. Since there's nothing stopping anyone from having a rectangle of area equals 0, b or n is 0 or both. However, if we want an area greater than 0, then both b and n greater than 0 must hold. We're not considering a negative area. Next, in column 1, knowing there are b number rectangular shapes, we can write it as a sequence S, and then rewrite it as a series W for finite sums. And then, using a property of numbers in the blue box, since there are b times shapes, we get column 2. Now, there are n times of them, such that we get the expression b times n. Lastly, letting b equal w and n equal L, therefore, by the commutative law for multiplication, w times L equals L times w, equals the area of a rectangle, the classic formula. Since both white boxes are a match, we're done. Taking it for granted. Finding the area of a triangle follows from that, because in case 1, we can divide a rectangle in the following way. The formula naturally follows. 1/2 times length times width equals 1/2 times base times height equals the area of a triangle. Seems straightforward enough, but what if we have a situation like case 2, we have an oblique triangle. Since we know we can calculate the area of a right triangle, we can divide the triangle in the following manner. We have the sum of the areas of triangles ABD and BCD. We then set up the formulas, substituting their bases and heights. It turns out we can factor 1/2 and BD. What's in the brackets, ladies and gentlemen? The sum equals the base of the original triangle. Nice. We can write it as 1/2 times AC times BD, which shows the formula for the area of an oblique triangle is the same as the formula for a right triangle. We're calling it Theorem 2 and a wrap-up. But what if we have a situation like case 3? We have another oblique triangle, but this time we can't divide it into two right triangles. Then let's consider it as a larger right triangle and then subtract the triangle shaded yellow. Sounds good? If it does, set up the formula as follows. 1/2 times AD times CD minus the area of the smaller triangle. In column 2, we can factor 1/2 times the height. Folks, what's in the brackets again? AD minus BD is just the base of the original triangle. We can write it 1/2 times AB times the height. Shows the formula for an area of a different kind of oblique triangle is the same as the formula for a triangle, which covers all cases of triangles. Then, Theorem 2 holds for all types of triangles. That's a definition of pretty sweet, because it's going to help us prove Thales' theorem. Alas, now let's discuss Thales' theorem. It regards the similarity between two triangles, such as triangles PBQ and ABC. Also, noting the lines PQ and AC are parallel. The theorem highlights the sides of similar triangles are going to be proportional. By that, we can put sides AB and BP into a ratio to make an equality with the ratio of BC over X. We can solve for X using mental math. We cross multiply, and as it turns out, X equals 10 over 3. Now we can solve for Y. Subtract 10 over 3 from 5, we get 5 over 3. Here's what we want to prove in the blue box. The ratio equality of BP over PA equals the ratio BQ over QC. Then we have 2 over 1 equals X over Y. To solve, we can turn the quotient into multiplication by taking the reciprocal of 5 over 3. We get 30 over 15, 2 equals 2, which makes the blue boxes match. For your interest, 10 over 3 equals 3.3 bar, where 3 bar repeats. 5 over 3 equals 1.6 bar, where 6 bar repeats. If it's true that Thales measured the height of a pyramid, then it's believed it's possible with the work he was studying. He would have used a corollary from the proportionality theorem, which is the ratio equality BA over BP equals AC over PQ. A corollary is a result that follows directly from another proven statement, usually a theorem. We're going to prove the corollaries in another video. Voila, here it is. Thales Theorem states, if a straight line is drawn parallel to one side of a triangle, then it divides the other two sides proportionally. Our straight line is PQ parallel to the line BC. Then we get the ratio equality of the sides AP over BP equals the ratio AQ over QC. Notice it has all the proportions of the macro and micro sets from our first discussion. The theorem also holds for a line PQ parallel with the line AB. Just visualizing it, it also holds for a line PQ parallel with the line AC. We want to find the area of the shaded orange. We also want to find the area of the shaded green. Finally, we want to find the area of the shaded yellow. So we want to prove the ratio equality in the white box. Here's what we can do first. Make a ratio of areas. By Theorem 2, we can make a perpendicular QH, the height for both triangles APQ and BPQ. The triangle BPQ is easier to see in the blue box. Then the formulas are set up in the following way. The area of APQ equals 1/2 times the base AP times the height QH. The same for the triangle BPQ. Nice. Let's solve the area ratio of APQ over BPQ. We can cancel the halves and the height. What we get looks promising. AP over BP. We list it for now. We'll come back to that later. For the remaining side, we just do the same. Make a ratio of areas. Again, by Theorem 2, we can make a perpendicular PN, the height for both triangles AQP and CQP. The triangle CQP is easier to see in the blue box. Then the formulas are set up in the following way. The area of AQP equals 1/2 times the base AQ times the height PN. The same for the triangle CQP. Let's solve the area ratio of AQP over CQP. Again, we can cancel the halves and the height. What we get looks very promising. AQ over QC. We list it and we're almost done. This is our favorite part of the proof. We know the areas of triangles APQ and AQP are equal, but what about the triangles BPQ and CQP? We can use axiom 2. Recall, the perpendicular distance between parallel lines is always constant, such that if you draw a line H perpendicular to one of the parallel lines, it will intersect the other parallel line at a constant length, which means the triangles BPQ and CQP share the same bases and heights. Can you see that? Then the ratio of their areas, QPB over PQC, will equal 1. It follows the triangles BPQ and CQP are equal. Since we know the ratio equality, APQ over BPQ equals the ratio AQP over CQP, we can name them A equals B respectively. Then name the ratios C and D as follows. We state we have that A equals B and A equals C. Then B equals C by axiom 1. And the extension, since B equals D and B equals C, again, by axiom 1, we conclude C equals D. Since the white boxes equal each other, therefore, Thales' theorem is shown to be true. To conclude, like we said, we want to prove the corollaries of the theorem in at least one video, and then do a study on how Thales could have used them to measure the height of a pyramid. So what do you think? Does the theorem have a resemblance to our first discussion? To simplify the relationship between the exocentric and egocentric perceptions, can we use the idea of proportion? If we think about it for a moment, put yourself in the middle of a road, standing in the middle of a base of a larger triangle where the point A equals the vanishing point, where the entire trapezoid BPQC is the microset and the triangle is the macroset. On this simplified level, clearly there's a relationship between the macro and micro. What do you think about the implications? Anything outside of 5 feet or 10 feet of the micro could be prone to illusion. We also have a relationship between BBQ and food for thought, with summer approaching, perhaps for another video.